So I'll hand straight over to Josh Darrall-Jones. Thank you.
Afternoon everyone, my name is Josh Darrall-Jones. I'm a strength and conditioning coach at Yorkshire Carnegie. Last 5 years within the academy and now in the first team. And my presentation is going to be on tracking individual development and determining real change. So the individual development side is going to be based around academy players, and then the determining real change will be applicable to sort of everyone. So overview of what I'm going to talk to you about today. So why do we need to track individual development? How you track it, and then what does the data actually mean when you've done whatever you want to do with it. So we track it because we basically want to be able to compare different players. So quite obviously these two players are in the same age group. One of them's about 130 kilos, one's about 40. So we want to see how those guys match up. So actually, does one guy outperform, does the big guy outperform the small guy? But actually, if they were the same, is one better than the other, or are they actually equally fit? If that makes sense. And then we want to be able to assess change over time or response to training. So that graph on there you'll see later, but that is 40-meter sprint time changes across the season. So we've got a pre-season, an end of pre-season, and then a mid-season testing. And within that, they've on average improved and then got worse again. But then we want to see how individuals have changed within that. So similar to what Greg touched on earlier with individual responses. So currently, most people in practice just look at absolute scores. So the graph on here is velocity of the 30-15 intermittent fitness test. So that's an aerobic conditioning test. And then the players on the left-hand side. So traditionally, the guys in green, they run the furthest or the fastest, therefore they're the best. The guys in red are the slowest, so they're the worst. It sort of makes sense. But then within that there, if we actually plot that against something that sort of makes sense, so that there is their 30-15 scores against body mass. If you look, the guys who scored really well are very, very light for the academy age groups. This is 3 years worth of under 18 data. The guys who scored poorly were actually very heavy in comparison to most of their counterparts. And then within that graph, you can see there's an almost certain negative relationship between body mass and 30-15. So basically, the heavier you get, in general, the worse you score on the test. So we almost want to be able to compare the heavy guys versus the small guys in the same age group. And then I'll show you how in a minute. So despite the fact that there's this relationship with the 30-15 and body mass, even within this group, there are two people of markedly different body masses who actually score the same speed. So on a piece of paper, they look as if they're equally as fit. But if you actually look at the difference, there's 50 kilos difference in body mass there. So one's a prop forward, I think one's a scrum half, but they've run the same speed. So we want to be able to compare those two players within our developmental pathway to see actually, is one outperforming the other? Is the heavy guy better because he's heavier and runs the same? Or is the lighter guy worse because he runs the same but is 50 kilos lighter? So we can do that using correction factors. This might get a little bit confusing, but bear with me. You need a bit of Excel expertise, not really, but we'll see how you go. So if you plot the same data in Excel, if you have all your data lined up in columns, all you have to do, if you find the log of each data point, so log of body mass, log of 30-15, that'll give you a regression line. And then we need that slope there, so that beta says minus 0.23. And that essentially means for every % increase in body mass, you reduce 30-15 performance by 0.23%. If that gives you a bit more context. So then using that, we can create a correction factor. And then within that, so in this example, I've used the average body mass of that whole group just to make it easier. So we use the average body mass, divide that by the player's body mass who you're scaling or correcting for, and then raise that to the power of the beta slope from the log-log pot. So from that there, the light player who's 69 kilos, his score's given a correction factor of 0.95. And the heavier player who's 118 kilos is given a correction factor of 1.08. So essentially there, we're multiplying the score we observed by their correction factor. And then that basically readjusts, so these two players are on the same level. So essentially, if the 69 kilo player was an exact scale replica of himself at 85 kilos, he's actually going to lose 2 levels on the 30-15 test, so he's down at 17 kilometers an hour now. If the 118 kilo player was an exact scale replica of himself at 85 kilos, he's increased his performance by 3 levels. So at the start, where they're exactly the same on paper, there's now 5 levels difference. And given that the smallest worthwhile change for a 30-15 is 1 level, if you take into account the smallest worthwhile change in the error, it's 1 kilometre an hour, that's a fairly substantial difference now between those 2 players. So even though what we observed suggests they're physiologically equivalent, they're actually not. And then I suppose we need to sort of understand what that data means. So essentially what I've explained to you there is that performance, if those 2 players are both at the same body mass, exact replicas, how would they actually perform? And then you can I don't know whether or not you can actually do this, but in my head it makes sense. You can sort of identify training targets from that. So from player 1, he's obviously 70 kilos. To progress through an under 18 pathway, he probably needs to be heavier, even if he's a scrum half. So let's say he needs to increase his mass to progress, but at the same time, he needs to maintain or increase his fitness. So then when he is heavier, he can express a certain level of fitness that we want. And then he can also work on his speed. The player 2, who's already 120 kilos, realistically probably doesn't need to increase any mass to push on to under 21 or probably even senior level. So our thought process for him is he needs to maintain his mass. He needs to maintain his fitness level because he's obviously very fit for his size, but then you can also work on his speed. So naturally, you've determined 2 things you want to sort of hold constant, and then a physical training factor you can work on that might improve his performance. So that is a sort of explanation of how you would compare players in the same age category, and whether or not this translates into senior rugby, still up for debate. Obviously, bigger, heavier guys are going to be slower, lighter guys are going to be faster. But within a development framework, we sort of want to know how one person fits within a group. So if that smaller player is going to be released because he was too small, actually, if we start looking at our data a bit better, we can say, actually, if he was this, he'd be at this level, and then vice versa for the heavier player, if that makes sense. And then the second part of the presentation is looking at determining real change. So in this part, we're going to look at the response to training. And then to determine real change, you need to run a reliability study. So this is with 40-metre sprint time. You assess a player. They have enough time period off where they can recover from the assessment, but where there's no physiological improvement or decrement. So you wouldn't assess them and then leave it 8 weeks to go again, because within 8 weeks you've probably trained speed and they've probably got better. So you want them to be pretty much similar on each day. So for this, we assessed, they had 72 hours rest, they assessed again. And then this gives you a CV percentage, which is the error. So that's the error of the test, including biological error in them, and the error of the equipment, and then a smallest worthwhile change in percent as well. And then that rating there is basically the interaction of the error and the smallest worthwhile change. So if your error is larger, essentially that rating marginal pretty much means you need to see a very, very large change before you can basically say it's real. And the graph below essentially is the grey bars are smallest worthwhile change, and then the data plotted on that is the change plus or minus the error. So you can see there that actually, until your change has been greater than the smallest worthwhile change and the error, you can't be sure that it's not within the error, if that makes sense. So the first change there, so they've improved by the smallest worthwhile change. So because the literature says 0.64%, they've improved 0.64%, we take that there, they've got better. But actually, they're only on the edge of the smallest worthwhile change, and the error suggests they could actually have got worse, if that makes sense. If they improve by the error, they're still not outside of that smallest worthwhile change, so they still overlap into that smallest worthwhile change. So even though they could have improved, we're still unsure whether or not they have improved. And then the third there is the smallest worthwhile change plus the CV. So they've improved the smallest worthwhile change, they've improved the error. So actually we're fairly sure with a 75% probability that that improvement is real. And then similar to Greg's presentation earlier, this is the 40-metre sprint time explained earlier. And essentially, if we look here, where they've improved their sprint time across pre-season, Everyone circled in green has improved greater than the smallest worthwhile change in the error. Excuse me. And then some people haven't. Some people are still crossing that threshold of smallest worthwhile change. So they haven't got worse because they haven't gone the opposite way. But they've stayed similar, and we're not sure if they've actually improved. And then if you look at the mid-season testing point there, the group mean average graph suggests everyone's pretty much returned back to baseline. So they've got worse from mid-season. There's unclear differences from the start of pre-season. So, like Greg alluded to earlier, the group mean data is really important and interesting because it gives you an idea of trends about how things change. But actually, even within that, there are 4 players who are still better off than the start of pre-season and 4 players who are worse. So, I suppose this is just a method that people can use, and it's actually fairly simple to do, where you can look at and track your players individually and actually start to have a bit more understanding of the error of your test and how people respond to training. And then just wrapping up, ask questions of your performance data for developmental players. The use of correction factors is easily done. And then you can track individual development to understand when a change is real and practically important. And that is me. Thank you.